very basics. So machine learning is basically a field which is quite interesting, and you could say that it's basically going from extreme theory. If you buy a machine learning book sometimes, you know, the thick books are just mathematical formulas. However, on the other end of the scale, it's extreme practice where mathematical even, you know, procedures end, where you break up functions which are one way basically, but you go the other way around, and support vectors and so forth. So it's a kind of interesting applied computer science field, bridging mathematics with real data which is out there. And with this, you have basically lots of overlaps with another term called data mining. And there's another one called statistical data mining. And there's another one called signal processing. So there are lots of terms which in the essence are all overlapping significantly in terms of what it captures. I've highlighted a little bit here the statistical parts of it because there are some tools and some foundations that we draw from statistics. So some of you have knowledge from statistics, like probability distributions or something. Okay, a couple of them. Yeah, don't worry, we don't assume too much in machine learning. That's the beauty of it. And that's quite also the difference when we come to statistics and machine learning. I will talk about this when we have the mathematical building blocks. But it's quite interesting also today because we have new technologies. And if you know a little bit now why it's a PRACE session, you think about, okay, there seem to be limits that we can overcome with parallelization. This could be memory limits, that could be CPU time limits, and so forth. Was traditionally not the case, but with the whole hype, I would say, of big data, we really have lots of big data now in Riedel. I have lots of example big brain data, Earth science time series, satellite time series, and so forth. So big data is there, and we have problems of using machine learning with it. So it's a quite an interesting time coming together to think about how it can fit into PRACE, what codes can be provided in PRACE, which are basically usable by users for different types of domains. Now, before we go in more details, a little bit another distinction between machine learning, because you have two major categories, where you say predictive tasks and descriptive tasks, which are quite important to think about when we capture the essence of machine learning. We really want to do predictions in the future, mostly. That means we want to have something what we learn now and can generalize to something we will see in the future. So we give predictions of the future. Some people of you know that already, credit card approval. So will this guy be credit worthy or not? That's a prediction of the future. I have lots of historical records from customers. But in order to know if this particular guy will do this in the future, I have no data. Right? How should I know the future? So I derive from my essence of the past, the historical records I have from other customers that are maybe similar, something about the future, which would be very much the prescribing or the predictive task I give then to the bank and say, well, this guy will default on credit, and this is very credit worthy, give you lots of money back. So these are applications in industry. The same you could do when you have some cell detection, right? In human brains, you want to have a kind of model of the human brain that would we do, and you do classification, what to predict, is this the same class of the tumor or not? I will come to this basically in some example later on. So this has to do with some variables, some explanatory independent variables, as it's called, in predictive tasks, while descriptive tasks are basically more something we know also from statistics, more summaries, relationships around the data, which could be also anomalies, which are quite important in time series to study. So these are kind of different fields, which have, of course, also overlaps in practice. But always think about that these basically will come up, and in many of the cases, we will really want to do this. Predictive tasks in machine learning, and there are some, of course, that would to do descriptive tasks that have lots of problems sometimes, not having the time to go into the deep details of the models. Okay, so having done that, coming again to this machine learning, what it is, and most notably these three prerequisites. So when you do machine learning, you basically always go there for some specific reason, right? And this reason is basically this one. If you think there's a pattern in the data you can find, then you do machine learning. So what you do is a kind of random number generator. Any idea?
Random number generator.
Yeah, so would you approach this with machine learning? Probably not, because it's random, there's no pattern, it's nothing to learn for, right? So basically you would have to have something in the data which you think like there's a pattern. And if you know the recommender engines, they're very similar, right? When you go for Facebook, on the right-hand side, you see lots of aspects which are very much according to your needs, or something you looked before, or something very similar that you would buy. This is all about this. So there's a pattern in the humans to know I would like to buy the red shoes, not the blue ones. Because I've done this in the past, looked at some things which are blue in the past, not on the red ones. So very simple things which you can actually determine in the pattern. And you don't need to know exactly what the pattern is, you just have to have a feeling for it, what could be in the data, what pattern is there. Then the second aspect of it is, especially here in PRACE, if we go to the simulation sciences, right, they have numerical laws, established physical laws, numerical methods like weather forecasts and so on. They have a precise formula, iterate over it, implement it, done. Right? Due to approximations, there are some errors and so on. But in the essence, they have a mathematical formula. They don't really need machine learning at that point in time. Right? Why should you do that? They just go ahead and implement the mathematical formula. We are different. We don't have really a formula. We want to create a formula. We create a function, so to speak. And this is something what you not really would do if you would want to go to machine learning. And then the second part really leads directly to the third. It's if you do this, you don't have a formula, you need something, and what you need is data. Right? If you don't have data, then you don't need to do machine learning, you don't need to do data mining. These things are very essential. So before you start with a machine learning project with an application field, always have these three prerequisites. Go them one by one through and think about what it means. I have a practical example later on. So the learning from data, again, the idea is not new. Today it's a term called data science, perhaps, which has quite some overlap of applied statistics, data mining, machine learning, signal processing. These kind of concepts partly that we have been reinvented in so many fields that it's a common essence today that we have here data science that we use in the research groups around and which are basically matter for PRACE here. And the problem that we have and the challenges with this is basically that the data is often complex. Now I start here with a very simple example and don't draw the conclusion that this would be the reality in practice. It's just to get you really from a very simple start. And we start with some look on examples of data collections. So if you now would have some time in the break or so, I encourage you to go to Pangaea. It's an Earth Science data repository. It's online. You can go there or you see references, or the machine learning repository, right? If you want to play around with data, I recommend this one. So you can use the tools that I present here during the day exactly tomorrow. So they're basically all open source. You can download them, use them. And I would recommend this one because it's already prepared, this machine learning repository, for the task we talked about, classification, clustering, and so forth. However, if you want to have a glimpse on the practice, how reality is in science and engineering, then go to Pangaea, and then you see really time measurements of ocean data, things which are not so obvious like the machine learning repository you basically see here. But the interesting thing is it's real data, and that's why it's quite interesting. Now coming from the 10,000 feet, maybe a little bit more, to concrete substance, where are now the methods, right, that we need in order to do something? And we have the three, let's say, different categories, whereby today I will mostly talk about classification because it captures mostly the essence of machine learning. Right? This is a very important fact, where you always have, let's say, some groups that are already existing and you have some new data and you want to predict, is this a red or a green class, for instance, in this picture. Right? This is a supervised approach. I have maybe already some examples I can learn from, and that's why it's quite the focus here. We will also focus a bit on clustering, just shortly, basically in lecture 2, to give you a feeling of another code that is existing that we can use in PRACE, called DataScan. Here it's not really obvious. I don't know really if these are different groups. However, with clustering mechanisms, they have distance measures. They have like tools in place that can actually get to this kind of conclusion that there must be two clusters. And DataScan and others are basically doing this as having the measurement of the distances between points and more smart actually rules that you can go for when we have the example of DataScan. Then the regression is something which is fairly trivial, although there's multivariate, so if you have, let's say, more interesting slopes and so on, not only kind of this one or this kind of interesting shape here, but it's a traditional model And it is a little bit different from the things that we do in classification, although sometimes you would maybe do first regression to get a good initial value of a decision boundary and then go to classification. It's not obvious directly to you, we'll see how that materializes when we go to the examples. But if you think about, you have known application field, you want to work on it, check the 3 prerequisites, and then it really goes off into this kind of 3 aspects. So where are the algorithms? And they are all basically partly in these kind of different categories. Then another part that I use often in the university and shows much success by the students is this CRISP model. I just want to introduce it briefly, and always on my slides you see where we are in the phases. It's a process model, and if you have a practical problem in your data mining field and you want to tackle it, I encourage you to use this structure. Right? It has this interesting process of having 6 steps. Firstly, understand the problem, then understanding the data, then prepare the data. And we'll see some examples with our simple example. Then you do the modeling. That's where actually machine learning is taking place. That's where we learn modeling. Of course, then, when we do the machine learning model, we want to evaluate it. Is it good? Has it good accuracy? Too much errors? Don't we generalize well out of sample? That is our major concern. We want to be good for unseen data in the future. If it's very bad, we maybe go back to the problem or this way and work massaging the data, better features, and so on. Before we get into the deployment, we put the system in the bank. It is running in practice and it gets all the customers right, predicting the stock market if you want. So reality is, with my students and with my teams and researchers, you go back and forth between all the stages. This is not like a water flow model from software engineering. It's really an integrated approach, but it's nice for documentation. You can have your nodes directly basically noted in the right parts, and you always can actually map the steps you do quite well. It comes from industry, so they have also worked long on it, and it's quite a good model to be adopted. So let's start with a simple application example, which is about flowers, right? And now the question is, why we need machine learning when we have biological experts? Right? One motivation would be to automate the process. And to automate the process means the biologist has more time. However, if you think now this is so easy, could someone of you think what this flower is? Is it a flower of type Iris setosa? It would be the red class here in this example, or the green class, the Iris virginica.
Green.
Why?
Because of the shape.
Okay. He is a biological expert. So who shares his opinion? It's hard to say, right? You basically could say it could be this or that class, right? And of course, biological experts maybe really have the clue and say, okay, when I look a little bit long on it, the leaf is like long and has some properties, and well, if you think about these, they're looking different, but these are longer, and this, you can go on and go on and go on and go on. So basically, you see, you need expert knowledge, right? That's the key essence of it. We call that partly labels. That's a term we will later materialize. So we know that these groups of data exist, but if you want to classify this flower, it's really something you want to basically classify, then you have to have something. You have to look on it, what is now the properties of the data. And this is where it starts when you really start with machine learning. You don't start with throwing machine learning algorithms on it. The first part, and often 60%, 70% part of machine learning tasks is working on the data, massaging the data, understanding the data, looking on labels, features, and so on. So in this particular example, it's a prediction task. We want to see, is this flower of that or this class? We basically see there, okay, there's a new iris flower, and it's a 2-class classification problem. That's a formalization we put here, so binary, very easy. Still, we have the question, what is now here in this picture, what could help us of determining whether it's this or that class, right? And this would be an interesting part to look at, so let's have a look. But before we, of course, go that way, you remember we should check if it's a machine learning problem at all, right? This is something what we have to think about. We thought, is there some pattern? And we believe if there are already some 2 classes from biologists, there must be a pattern, right? Otherwise, they cannot classify them. So there is a pattern. And somehow this influences the type, apparently. And for the non-biological expert, I put here the petal and the sepal width, which is sepal is this leaf and petal is this leaf, interestingly enough. And there seem to be, depending on this site and width, that this somehow influences the time. So there is a pattern to discover. However, you agree with me that there is no physical formula, like in our simulation sciences, of saying this is a numerical law that I can use with numerical methods to actually get to a solution of telling me this is a flower of this type. So there is no mathematical formula. Okay, that's very great. Now we have the second prerequisite for machine learning. Now we need data, and this is in the UCI machine learning repository for you to play around. Right? If you don't know it, you can directly start tomorrow if you want with the knowledge you have here in the course. There are some samples, 150 data points. We call that samples. Now, labeled means in machine learning, we know which class it is. And this is an important effect in supervised learning that we can actually learn from that. If you wouldn't have the samples labeled, we still can use unsupervised learning. So it would not be hopeless. But still, it's much better to have labels, always a learning task, because they give you concrete ground to stand on. Think about exam questions you want to prepare for exam, and you have some test exams with some answers. If you don't have the test exam answers, if you don't have the test exam, you don't really have some ground to stand on to be prepared for the exam. So it's balanced. That's an interesting property. That means like 50 samples per class. And we have seen basically it's a two-class problem. And it will later come to you, it's actually a three-class problem. And I put here just the emphasis on two classes. You see it's like 150 samples, but there are three classes in it. And I just picked two to make a certain point for you to learn the linear separability. Later we will get back to the third class and integrate it and see that linear separability is also not the case. And obvious to you just as a side remark. So we will look on this interesting flower properties, which are sepal lengths, beta lengths, and so on, which is basically the attributes. We also would go towards features. So that was a term called features about the data we have. And then, of course, we have the labels. So this is iricitosa, vesicular, or virginica. So the three-class problem. However, for the sake of understanding, we start with just picking two. Of course, then you go forward with a practical machine learning and data mining project. You would check all the metadata you have, right? Always important. And more these days, metadata is available. You know who was creating it, the author of the source you have to quote when you work on it. You know a little bit about the samples and instances, very useful if you go for machine learning, for training and testing sets. I will talk about this later to differentiate a little bit on it. And then you know a little bit about the attributes. So they are apparently numeric, it's very obvious because it's about length and width and so on. And then there's this predictive attribute, which we said is a class. And what we want to achieve now is we learn from these 150 samples basically what we have already in the database. And every time I go into the field, I make a photo of this interesting flower, which is blue and looks like an iris. Then I know exactly which class it is, because I have already a learning model, some system, really a kind of system in form of developed with computer science, technology, software engineering methods to be useful. And this would then predict exactly which of these classes it is, right? So looking on this practically, some people have heard from R or Riedel. So I use this mostly in practice. Okay, R and Riedel is quite often used in statistics and also machine learning to work on data, but in a serial fashion. And that's a big problem. There are some additions to parallelization, but it's not really so well like MPI, OpenMP, and like things we use in PRACE. So in this sense, you would look a little bit on the data. You don't look on each value specifically, right? There is no time for that. And 150 here is a digestible few, but if you go to a practical solution, it would be thousands. So you don't want to do that. But still, of course, you have to understand a little bit what your classifier is doing. Right, so what is here the predictive attribute? As you see, it's like attributes in terms of text, and then you have here apparently some interesting error. Because in some of the tools, you basically load it in, and the first line is always taken as basically just a kind of metadata part. But as you see, this is one showstopper often. Check this. The first line is actually here real data, and this goes on and on in different MATLAB, in different Riedel. RStudio and in different tools you use, this will again and again be a kind of small problem that you run to. Still, you see the same things we have theoretically looked at, you will find here again, with having all the four values, basically here, and then the class of which type it is. Right, so far so good. No questions? Good. So we understand the data in some clever tools like Riedel here. It's a GUI for R. You can just, say it's a header, and then you basically remove the first line, and then you have here basically the correct header, and the first really is already the data. That's a kind of minor aspect. Still needs to be checked always to assume you have the right data. And also what I said, like we want to pick a two-class problem here. And in this particular course, it's to make a certain point about decision boundaries, linear separability. So the other basically word we're talking about is sampling. You will hear a lot of samples. So that means nothing else than having data items. And each of them would be, let's say, one of it. And if you pick a couple of them, you have a sample of this. And it will relate a little bit to out of sample and in sample. So what you see here basically is in sample, right? That's data we have in sample. So we learn from this, from the IRIS data set, and then we want to have out of sample something we will never know, we never see. It's somewhere in the field. I go outside here and maybe found an IRIS flower. I'm not sure if they're in Cyprus, but that's the out of sample performance that we want to. We generalize out of sample. And here we also sampling just for the two-class problem 50 out, basically leave them behind and just pick, let's say, two classes here from the three we have available. The reason I come to, but this is a word that you should also know by heart, sampling. And there's, diversity-based sampling. There are lots of sampling strategies in real practical scenarios. But for a beginner course, it's really something you have to know. And then, we believe there's a pattern in the data. You can then play around and do some more feature selection. And features is a very loaded word. It will be with us all the 3 lectures, and particularly will be important in lecture 3. Deep learning is all about feature learning and so forth. So this feature selection just basically says you could, think about that machine learning maybe don't need all the features in the data. It's not always wise to use all the data features because they implement, lots of mathematics, and with this need computational power. And with, dropping some features which may be not important for the classifier, you have to still, test this and work with this if it's really the case. But maybe there's a process when you select a couple of few. And again, we will see all that materialize when we have lecture 2 and 3 more other examples. And then you would do something like we call feature selection to just prepare some of them. So there's another process called feature extraction or feature engineering where you create even more features. This is something what we'll do in lecture 2, right? But here we kind of downsample in this direction to 100. And then in this direction, if you want, you could say, now I really want to have, not all this 4, I just want to have these 2 numerical values. Right? Also clear? Think? Okay. And now we play around. So coming more to the more formalization of that, right? To get more to machine learning, to the ideas behind it. You have this data set plotted, typical scatter plot, nothing very particularly, but there is a nice property, right? So if you look about this and this, we see already that when we use this data set that we just have here and visualize it, there seems to be a pattern, right? So that's something like, okay, this particular flower seems to start with a petal width somewhere with 1.5, and here the other flower seems to be very, very small. Everything is just, 0.5, 2. So there is a pattern to be discovered. And we would formalize this data set here that each of these interesting points now will be an X vector, which captures the essence of being multidimensional. Now on a 2D problem, this is just one-dimensional, right? It's one dot. But if you think about machine learning and where the power is, it can be going to multidimensional problems, right? Always think about that. Basically, each of this interesting data set that you have, each flower entry that you have here, is a vector, right? Which is X, and then you would have the different dimensions, which are here, for instance, in the 2 dimensions. It would be a dot being this. And this is your data set, and we always will talk about n samples. That would be important for the theory to think about, and also for the big data problem. N is a loaded term. We will reiterate in lecture 2 when we come to HPC and so forth. So we know there's a pattern here, and this will be our terminology when we go through. And then, because we have already this class information, you can go on and color them, because there was some label in the data. This is always Y. And it could be the class of this one or this one. So you basically end up with your data set being this. X1 is a vector of one particular point, and it will tell you, is it a red or green point? Right? And please omit this stuff, this is just an error of visualization here. But basically you always know, okay, I am this or that class, like we had in the overview. Very easy, go, and still no machine learning so far. So what we want to have as machine learning now would be, is there something we can establish that would differentiate automatically these two paradigms? You could have several ideas, making it fixed, of saying, looking at the data now, and you would say 1, everything above, and everything below, right? But think about, again, for machine learning would be a complex problem where that would be not so easy to do. And also, you want to automate the process, right? You don't want to spend time looking on this data. You get your tea outside or your coffee, and the machine learning will do that for you. And when you come back, you have already a model that actually can differentiate between these two, and you just have a new flower, putting in it, and it does the job for you. That is the idea where we're going. There was a question, yeah.
What about when these two groups are very close and they have cross sections?
Very good point. That is actually what we captured in lecture 2. It's linear, not linear separability. This is a linear separability data set. So very beautiful. That's why I take it in the beginning. We will take the other part in the lecture 2 where I come back. It's actually a problem which you have so often in practice. But to make a certain point here and to keep it easy in the beginning, I would like to keep them separated. Here. So we have now the question of testing and the modeling. We want to create this modeling. There's a new data point. Does it belong here or does it belong here? That's our key question. We formulate. And there's something what we want to establish as a term, which is a decision boundary, to say, can we have a line here, decision, right? Is it this line, this up is red, this line down is green? And we see how that can materialize this decision boundary by using a very, very simple mathematical model called the perceptron. So you can model this already basically intuitively of saying you basically have a decision boundary which is like this, and you would have all the kind of vector parts that you have, so the properties in your x vector, and you would basically say, okay, you multiply this by a certain weight, that's what you learn, to actually think about and moving around this little interesting decision boundary here. And then you would say there's a certain threshold where you say, well, everything above it would be red, and everything below it would be green. Right? And there's a compact notation that you basically can use here when you do this, and if you put the threshold basically inside the learning part. We come to this also in the next one, where you just think like the attributes are important, you use them in some weighting scheme, right? Because that's the only thing you have, data. So with the data, you weight the data, how it's important it is to create and helping this line. So there's a mechanism that's helping us, which is basically then the perceptron learning model. But essentially, this model will do something like this. It will create a decision space of saying, right, all of this would be this class, and all of this would be that class. So this is another example. Just think about, of course, we are going to something which is a line, an equation. And you have always this vector x1 and x2, which you help you basically to establish the model. So what we want to learn really would be this coefficients, right?
How they are related to the problem? Why they are independent points?
Independent.
Why they depend on particular points? How they come from?
The weights,
Yes.
or
Yes.
basically that's the model.
We don't have them. We have them in the points.
Right, right.
And
But
we introduce them. So what is the physical? What is the reason? Why we relate them to each point and not to each class? I would think they would be related to each class, not to each point.
yeah, this will come in the point like when you have the learning algorithm. So this, what we have here established is just a decision algorithm. There's no machine learning yet. Right? I will come to this now when we come to the machine learning algorithm. It just established that you have a decision which is a line here. Right? And now we learn this 2 and 3 and 1, this coefficients of this model. And the reason why this is done is actually because the pattern in the data. There will be strong patterns in one of the attributes, which gives them a lot of weight. Now, credit card approval, for instance, if you have your residence for 10 years, would be a very strong weight. If you have a residence for 1 month, would be a very weak weight. That's where the relationship for the data comes from. And this will help you draw a line, which is in a multidimensional problem or a slow phase, of course.
So the WUs in the previous slide, the WI, they are related to the properties and features and not the points.
Well, the point is the feature in the end, right? So the points are
Not the
are a vector.
not the data sets.
Right, yeah, but each of these points here
Yes.
is X, and this has the features,
Yes.
right? And in our case, it was a very simple one. It was just the width was one feature, and then the fatal length was another feature, right? And with this, you iterate through the features and give them certain weights,
Okay.
W. And with this, you're able to think about, okay, that this somehow seems to be very much important if you have a very high property in one of the features being below 1 or being above 1. So this is something already to learn from. And this is just the next one that you see here. It's just an example of saying, this is what we aim for, a line. It could be any line. It could be up, down, ascending, descending. Right? Just to get you the notion of a decision space and decision line. So how we get there, how we learn that will be now something that we learn with the perceptual learning algorithm. Right, so now we have this algorithm. There was a question here.
How to do these coefficients?
That's what we now cover. Right, so this will be all about it. The perceptual learning algorithm. When you think about what I just put here, the intuitive notion was very easy. We just give them different weights. We have a threshold. If you remember how the typical line equation is, it's very simple. It has a bias, so to speak, and a threshold. And you actually can come to a compact notation. You put this in vector form. You have your training data. And now what is inspired in the perceptron, which is really very old, you see 1957, that's the first basically learning model that you can think of. And it will always fire with one class or will not fire with another class. And that's how you get the relationship to the classes, right? Because you model now with an activation function, sometimes sigmoid, sometimes others. In the case of red, I fire, let's say 1. In the case of green, I don't fire. And this is what you optimize now, iteratively. And now we come to the machining process. That's why machine learning over iterations. There's no direct solution for this problem, right? You have different data. You need to learn these weights, which would be basically the input nodes to a typical perceptron. It's inspired from biology and neuron. We will see how that materializes in lecture 3 much more when we talk about deep learning. But this is a very simple learning method. And when you go iteratively over them, you will see that you can learn weights that actually satisfy this. So that y would be 1 and y would be 0. Or 1 would be iris setosa, 0 would be iris virginica. That's where we want to. And we have this data available. Remember, we know when to fire. We know x. These are the constants. That is your data set. Right? Of course, you need some constants to learn something. And this would be the only thing we can learn here. Because we have the data, which is constant. And in this sense, you can go on and create this. And here's just one example again for you. That, for instance, here in this interesting example of this data set, this can actually be learned. So you have the sign function where you just say, here, my predictive variable basically I want to have is -1 or +1. Very simple. Right, which is the sign, plus or minus. And then you basically learn iteratively over this in the training phase, which we call training phase, later there's the testing phase. And eventually, in the end, you will up with these interesting weights. And you can prove this with this data set. If you have 4 going in as x1, it would be 1, 0.3, 0.3 firing, all of them will fire. And then we'll give you something which is higher, basically, than, not negative. But if you have something like here, for instance, you would say there's nothing which would fire, and you have a -1, then of course, you're basically automatically negative. And in this sense, you basically can see, because you subtract the threshold, that's why you're negative in the end, right? Which is always 0.4, so you are in the minus space, -1 is a sign. So then this is something which is a very simple, the simplest learning algorithm. Still, there's a question mark, what is this, right? Machine learning. So where is the training process here? And you can basically see, and here to the tests, that this is actually true. We did this already. But interesting for us is now how we come to this line, right? We now said, okay, this is possible, and we have the attributes in the data set that give us something, and the guiding output y. So the interesting thing is now that what we do is we play around with this line, right? That's what we can do. But it will go over line and have different positions, so there's not something we can just pick. We will see in support vector machines as a principal mechanism how we can pick. But here in the perceptron that's not possible, so we have to iterate overall wrong classification, that's the idea, to see how actually this line is then getting to different hypotheses. And this is actually what is done when you play with the weights. When you know a little about mathematics, and now it's like, don't get scared away with transpose and everything, and dot products. It's basically just a nice notation, a bit more compact. If you think about this, what we had, and put here the W0, which was our threshold, and put it then basically together and say it will be always 1. That's a kind of simple part or simple trick we do. We can write it in a vector of 4, right? Which is here then W is here in bold, and X, which means vector representations of that. Right? You have 0, 1, 2, 3, da 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 da. Now what transpose is doing of doing this dot product is nothing else than saying I have this vector multiplied basically, and then with the x's here, but I can only do that when I take the transpose. It's nothing else that you see there in order to take wi1 multiplied with xi1 and so on. So it's a compact notation that people use in machine learning to make some things much more simpler. It's equivalent to this, right? We still do the sign of all the vectors, dot product, and so forth. There's another reason behind the dot product. Again, basically, when you come to machine learning, this would be interesting notations. That's why I shortly provide you with a glimpse on that. This dot product, which is basically the same that we have seen in vector form, is interesting, and in more ways than one. One of it is it's a scalar to come out. And it will be an interesting property if you want to understand support vector machines. We don't have time in this course because it takes 2-3 lectures to understand support vector machines with kernel methods completely. But we will, let's say, have some in the appendix if you want to learn more, and we'll cover it briefly, basically in the lecture 2. But this is an interesting property, and it has some projection capabilities, which then gives us some distance, basically, over space. Again, a nice property if you want to do support vector machines. Now, as part of this first lecture, it will be not so important, but we'll come to that shortly, basically, when we have lecture 2. And now, basically, what the machine learning step is in this perceptron learning algorithm. The first simple learning algorithm we cover is you pick one misclassified training point. You can always test, right? You have your boundary, your line. You take a red line, oh, it's in the green space. It's behind on the other side. So you play around with this line. And this is an algorithm which is very hectic and has not necessarily very good performance, but it has a distinct advantage of converging. So if you have linear separable data, you have really two classes which are separate, not the case you mentioned, but the other way where you have two classes which are not overlapping, then it's guaranteed to converge. And the only thing it does basically is takes any time you misclassify point, this is your label, and subtracting or adding with what's coming out according to this rule, right? If you have a negative, you subtract. If you have a positive, you make an addition. And with this line will hop around wildly, and I have an animation for you to see that. And it will terminate, of course, when there's no next misclassified point to pick. And this is the essence of all this learning algorithm. And with this, and I'll provide you a video shortly, and this is what you then basically can use once you have established this line, right? For all this up and downs, and suddenly there's no misclassified point. Then you have this decision boundary created in a very principled way, looking on your data. You learn from data, have created this line, very simple model, admittedly, but it learns. And you don't have to put this data there. It has learned this automatically, right? You were outside drinking your coffee. You come back, the line was created by the machine learning algorithm. Very nice. And the first, let's say, substantial takeaway message that this can actually be done. So let me give you a small video how this perceptual learning works in practice. So you would have this interesting data set here, and you see how this algorithm is now playing around. with this interesting decision boundary. It doesn't find them directly, and here we assume that it is linearly separable. But again, if it really would overlap and there would be a red point here or a blue point here, it would not work. It would not converge. It would always have a misclassified point. A big problem of the linear learning model. It's not really prepared, this perceptron learning model, for data which is not linearly separable. But over time, it's now basically guaranteed it will find the correct line and will then basically report this line. And this is nothing else than having the weights learned for a mathematical equation which is just a line. So much for the magic of machine learning. Any questions maybe, because we have done the first part? Yeah.
As I understand, this boundary, decision boundary, I can get from the perceptron training. But perceptron training model is a human decision. Yes. How can I train? How I will train this perceptrons neural nets? It's on my decision. Yes. It's not automated.
Oh, it is automated. No, this actually can be implemented. Right? This is not
algorithm. That's training process. It is how can I train? How the neural network perceptors. It's all human decisions, not magic. Yes.
No, it's completely in the data. You don't do anything with it. The only thing you have is guiding output. So sometimes some people have said this already with a Y, that this is a red and this is a green. That's what you need. And the other thing, then you just apply this sample update to this rule. Iterate with your computer again and again over it, and until you have no misclassified models. Because you can always, of course, check this, right? Is it equal when you have the Y or not? So it's something what the computer is doing. It's not the human. And the same would be then for neural networks. It's a much more complicated model. We have different perceptrons. We see that in lecture 3. But it will be automated, and it's an algorithm you can implement right now. And there are probably also, if you look in the internet, some implementations of it. If you have some data, automatically will be learn these kind of weights with this simple update rule on the weights. It will be not the perfect accuracy, but it will converge and give you a learning model. Another question. But the principle of machine learning is a bit clear now, yeah? Okay, good. So let's go to more sophisticated stuff. What means learning? So now we can think about that learning. What we have seen so far was very supervised, right? So we had this idea that there was a Y that was guiding us. Is it a red or is it a green? This was Y, it's supervising input. You don't have that always in practice. You have sometimes unsupervised learning problems, right? Where we know this a bit from the vending machines, for instance, throwing in a coin. The machine has no idea what coin will come, but it has some indication, the weight, right? And the size of the coin. And so with this, it's able to really learn basically from it what kind of coin it is. And then there's a third way, which is a human way of learning, of reinforcement learning, just for the sake of complexity, where it is then, basically like a human, you would learn something through iterative developments. That's something which are the 3 learning parts. Let's cover them briefly, because it will be important then also in the lecture 2 for looking at some different problems. You would always have this input, that is your data set, with the different dimensions.
I didn't hear what it was.
And then you basically have the guiding output, Y, which would be your label. That makes it supervised. As if an instructor would always say, for this type of input data, this D can be very long, right? 200 dimensions, 300 dimensions. So then it would be not obvious as a human to do this decision anymore. You need a machinery. And then you would always have this data. And then you can do, prediction, inference, not so important right now, but you have this kind of guiding output. And this is an example we already have in this context. However, I want to give you, just for the sake of complexity, also the 2 other pointers. You can do also learning if you have no output data, right? And this would be then unsupervised searching relationships in the data, like I put in the beginning, like the distance measures between points. Some points will be very closely together, others will be very far apart. You can create groups from them. That's what we will do in DBSC and also in the second one. And of course, it's more challenging because you have no guiding output, nothing you really can help you with. still there's a pattern in the data we can learn, and which would be the distance measure. Yeah,
But
please.
it seems to me that it's a different problem. This problem is the problem of creating the groups. The other is to classify a point to an existing group.
Absolutely.
So it's a different problem.
That's right. It's a different learning approach,
Okay. Yeah.
right? However, I have to say sometimes you would do basically that's unsupervised learning before you do the supervised learning. To learn features here, it's unsupervised learning. When you think about, okay, now I have an idea of groups, now I learned the groups, and now I can classify new points, right? And with this, you have the different mechanisms. Clustering goes very unsupervised, but you can do it also supervised. So this is a different level, right? Algorithms, and these are completely learning approaches we're going to. We can also do classification in an unsupervised manner, also possible. However, would be not so trivial as in the supervised learning. All what I'm getting to is what data do you have? Right? That's a key essence. In supervised mode, I have input, output. I can learn from that very easy. Then here I have just data. I have no idea. But of course, inspecting the data and then looking around and think, okay, there could be potentially groups in the data. Let's find something, and then you get to something which is fairly interesting and could be done with clustering, but also with other mechanisms. And then you have a distinct group created as pattern. Is that a question in the back, or?
Cohoming maps are supervised, isn't it?
Sorry?
Cohoming maps.
Well, it depends. You mean convolution maps?
Cohoming maps.
Coordinate maps. I think there are also unsupervised versions of them, I'm sure. There's always some tweak, or you do unsupervised before you do something like this with that maps. And it's like a practical problem in a sense. You have to have always this. That's what you start with. If you don't have labels, you're automatically going to the unsupervised learning, right? So one example, we have brain data where we don't have anything, right? So we would say, but if you look on this, and this is different, this is what we want to, right? It's fake. It says the brain, it's just a part of the brain at the edge. It has different layers. The layers actually are related to functions of the human brain and so forth. There is no mathematical formula that says this layer starts there, this layer starts there, this layer starts blah, blah, blah. So what we do is have distance measures between the cells of the human brain cuts. Right? So we cut a brain, we have 700 slices. We look on it on a microscope really and see something like this. So there is a pattern to discover, and the expert sees that. Right? When the expert is looking at this, on the microscope he says, wow, here are two different layers. However, we do this for a very high resolution brains, very huge, and would take enormously time for the scientists of doing this with 700 slices to reconstruct the 3D surface of these interesting layers. So we need to automate the process. So this is an idea where you do it completely unsupervised, basically, right? You could start supervising, but there is no supervisor that has time for it, to look on all this human brain data, mark it explicitly, when and what pixel exactly now will be, let's say, this or that layer study. However, we know by looking at it manually on one of the slices, there is a pattern to be discovered. However, you quickly learn that there are problems, and these are related to the question that you just provided. There are overlaps, and this is a key problem we will face later on. And that's also where unsupervised techniques have lots of problems. Right here, it's very clear and, let's say, very simple. There would be probably 3 groups because there's no overlaps. Very easy to find it unsupervised. Here you already are in question. And this will be always together, when you do practical problems like the brain, here we have the same, always related. There's some layers which are very easy to be determined, some others where it's a new layer, or is it already one layer? You don't really know. And this is a problem of unsupervised learning in a way. So just to contrast it with reinforcement learning, and this is, let's say, very famous normally from backgammon and so on, where people have learned from previous backgammon games and can now play backgammon better than the masters in backgammon. So later on we will have the Go, but this was deep learning in the lecture 3. Here you have also data and some output, and this is not the correct output, unfortunately, but it gives you a grade of output. So when you think about the toddler example, which is very famous in the machine learning community, the toddler will come to your tub and will see, oh, it's very hot, and there's smoke, lots of it. So there's a grade of saying, oh, the pain is like this. Now when I do this again, I come and there's less smoke, the pain is less, because probably the heat is less. And that's how human learns not to touch a cup. And the idea is the same with reinforcement learning. And this is by most applied to learning games and this kind of thing, not so much in machine learning problems in science and engineering. They rather go supervised and unsupervised ways. So then, to make a summary about terminologies, because that is an important factor when we go further. We have this target function, something that we try now to create. We have learned a line. That is a function, if you remember from mathematics. So we have a labeled data set with samples, right? In sample, that's what we have. Each one was a vector with several features in the dimension d, and always a guiding input output, y, up to your whole sample n. So what we still want to do is to create a system that works well out of this. So what happens when basically I get a new data point, which is the notion of out of sample. That's in sample, we need to know out of sample performance. And for this we need learning theory a little bit to say, can we actually say something from this about that? And this relates to probability, something about statistics, what we basically derive from this field. Then there would be a training set and a test set that we need in the modeling and evaluation phases, and we'll come to it. The training is always done on the training set. And then you have a training system, but of course you want to evaluate your system with a test set. So you start with breaking down this data that you have here in different sets. And throw, as I said to my students always, throw the test set in the corner, you will forget about it. Right? You don't touch it, you just train. And then you work on the data, train the system, and at the end, when you're very sure you have basically trained your system, everything is established, you take the test set out, and then basically can do the machinery and see, is it good accuracy, is it a bad accuracy, go back. So let's see how that materializes. There are different phases in learning, that's what I wanted to tell you about you. And this is really the training where all the machine learning takes place, the learning is training. We have these training samples though, which are limited, finite. Right? You pick a few, but now there's a question how much you will pick. And this is something which is related often to use cases. There is a typical rule of thumb, if you basically have enough data, when you think you can learn well, take less for training as best as possible, like 10% for training. Right? With this, you have a very good guarantee that when you train and you test it with this kind of out-of-sample expectation, then you have a very good system. Right? That's why you always have this two kind of them. But it really depends on your application problem. It's an application domain question. When you don't have enough training samples, you cannot really learn. Right? If you have a test exam and I give you as a teacher one question in the test exam, there's nothing much to learn from, right? When I give you a test exam with 50 questions from the exam, there's more to learn from how the exam would be. So this is something also related to this. You don't pick training set data too less, because then you are not able to learn. On the other hand, if you take too much of the training set and you have less for test, you memorize the data rather than having anything to test your data. Right? And this is something which is also bad, because what we want to do is to generalize out of sample, to see something which we then just can approximate with a test set. So that's a very rule of thumb, if you want. And again, an interesting point where machine learning is at the end in terms of mathematics. There is not a proven number you can use for this, right? That's why it's applied field also. You have to think about your application domain problem. Then when you go to the evaluation, I already said this with the line that you established, of course, very simple. There's a confusion matrix, as it is called. You have your data set, right, which has the x vector and always a given y. You can iterate through this and create this interesting matrix that you see here, that the actual prediction was basically like this, or basically it was the other class, so it was wrong. And so basically this is something what we could use in always point-wise. And this is an interesting notion for the second lecture, because point-wise means always nicely parallel. So here we don't need necessarily massively parallel MPI, lots of complication. You can do this per point. You have always this kind of one and one, another one, another one. While the machine learning process of learning before always needs the data to establish a model, so it needs the whole data. So this already points to some benefits to the parallelization lecture we will go in lecture 2. And then there are just two kind of notions that you should know when you use this confusion matrix. of the classifier that you can easily create. There's some term called accuracy, which is nothing else than the number of correct predictions, number of the total predictions, a percentage value if you want. And some people also put error rate, although that is less used, mostly it's used the accuracy, that's how it was found. In machine learning problems, however, you will see that in rare cases you have 100%. And you would even go that far, you have never 100%. And this is not obvious to you, we will see how that materialize when we talk about noise in the data. There's some certain aspects in the data, noise that you cannot learn. Either your model is not good enough for learning it, or there's some measurement error, whatever, from a kind of measurement device and so forth. We will talk about that, but please go away after this course and not get the notion that when you talk to your boss, you cannot predict 100% the stock market, right? And also when you go to another application domain field, you will have 80%, 70% accuracy, not 100%. Right? And this has many reasons. One of the reasons is that data, for instance, is not linearly separable. As we have seen, we could imagine already when this is not the case, how do you do a line there if it's not linearly separable? So there must be some errors allowed for a model. And this will be related to some of the things we're talking about. However, if, of course, the accuracy is 80% and you have nothing before, it could be quite well. You automate the process of looking at data. Lots of data gets untouched. If you go to Pangaea, it's 90% underutilized. Scientists have no time. Measurement devices are easy to create, everybody measures, but to look on the data is very tricky. So doing it automatically, getting 80% performance is better than having zero knowledge. Right? And this is already one benefit of machine learning. And then, of course, when you think about the time-consuming process of looking for all the labels from the unsupervised point of view, maybe for a biologist in the field of flowers, if you get 80% right, it's already perhaps a good starting point. So you can just check more quickly, is this right, is this correct? Okay, yeah, it seems to be exactly right. So the time you help in automating the process of letting machines do the work helps also the humans of helping then, with the correct labels and so forth. Okay, so let's go a little bit more than formalization of what we talked about. And we start with this quite interesting formalization where we said, okay, we have these different points here, everybody is getting output, we have samples. Now we want to create a real diagram to have basically a real picture in your head how machine learning works. And we do this with a supervised fashion because it has a nice property with the formalization. Unsupervised is a little bit less formal, and so you don't have so much guiding light. So we took the supervised learning here to give you really something concrete at hand that you can always play if you have a practical application problem. And when you go here, you basically go to the training examples, you have them, as we discussed, this could be anything, which is there for your application domain question. Historical records of customers, could be ground truth data from satellite images having land cover classified. Is it a water, is it a tree, and so forth. Remote sensing is what we will cover in the second lecture. Could be any example that gives you this, basically, that's where it starts, right? If you don't have this, you don't need to start. And we want to work with this. And we have learned that basically the feasibility of learning seems to be, and we have to still establish that it's feasible to learn. This is what the theory will be about later on. We will learn an unknown target function, right? Which was a linear model we had in our simple case, but we want to have a linear function learned. However, there's a problem. What we would say, we never learn this ideal function. Otherwise, we would have 100%. So we have an approximation that we learn, and we will never learn this unknown target function. We just try to go towards it. Right? Let's put that in a diagram so that you have an overview. And we will create this diagram now and look on this right side because it gives you a notion what you can do, what you cannot do. So we have this ideal function that we will never know. So it's very bad, but we will have some machine learning tricks to go to it. It created apparently this training examples, right? It's a mathematical formalization. So we know there must be something creating these examples. However, we want to approximate it. So this is the first part of our learning algorithms, and that is something what we need to have to go for. We don't need to know this because this is something we want to approximate, we want to go to this. And some people have maybe heard from function approximation. Some people know that word. So that's something very similar what we do in machine learning. However, we go one step further, saying we can even have functions which are not mathematical. And that is, of course, a question mark because mathematical functions are mathematical. So there will be something called probability that helps us to the rescue. One example, just again, the function that we learned was basically this interesting property, which is nothing else than the line formula we have learned to create this one. So this is our function that we try to learn. However, the ideal function we not learn. So what can we do against it? Right? Because it could be different ones. It could be different functions all creating this. We have no idea. So which one is the one where we think it would be best, and we approximate this. So this is something what we will not possible to do, but, and this is now the interesting part of machine learning where it starts. We have a tool set, a hypothesis set in our pocket. We know some candidate functions. So when I see a machine learning problem, I have a hypothesis and say, this is a linear learning problem, when it's simple. When I go to another problem, I say, well, here we need support vector machines, deep learning, or artificial neural networks. So all of these are hypothesis sets. Models, which are nothing else than the line, the perceptron learning model would be one. And what we want to do is we want to approximate a function that I call G, which is approximately f. It will never be equaling f, as we said, otherwise we'll have 100%. Right? But we will iterate through all the different hypotheses, pick the best, which is G in our mind, and this would be the one we say, this would be the certain boundary. It will probably approximately, approximate that very well. So let's put that in our learning diagram. Right? So we start from the bottom. That's what we have, our tool set, what we learn in machine learning. Artificial neural network models, perceptron models, deep learning models, and so on. The final hypothesis is something what we still have to figure out. It should be something close to the ideal function that we will never know. Right? So how we do this? Algorithms, as we learned already. So we have seen this linear boundary can be established in a systematic way by learning through the algorithm. And we had the simple learning algorithm, which was just the perceptron playing around with the vector up and down, very tedious, 10,000 iterations, 20 up, and suddenly no misclassified point. It seems to be a line that helps. So we pick this one, report it as G. It is the one that from all these different lines that you have, these are all different hypotheses, all different lines. Right? Hypothesis 1, 2, 3 in the set. All of them are possible. But one of them will be picked by the algorithm that we will report G, which then approximates F to a certain degree. At least we have not misclassified points, so it's very good in approximation. Now this together now is called the learning model, right? So you will always have basically the idea, which is a perceptron learning model idea of the hypothesis set, but you always need an algorithm to train the system, something actively, you go through the data, harvest the data, implement something. This together then would be then what you basically do and report as the learning model that you basically use. And the perceptron is of course a very trivial one, but still it does a job, right? Especially for this little data that we have. And this is the solution tools. If you go now and have a package for implementation, you will find the perceptron, and there will be definitely the PLA, the perceptron learning algorithm implemented with it. Otherwise the perceptron will be useless. If you go to support vector machines, there will be quadratic programming with it. Otherwise, you don't need support vector machines. So sequential minimal optimization, all is inside the package. If you go to artificial neural networks, you would have back propagation with it. Back propagation is the algorithm to learn an artificial neural network. All of this is basically a solution tool set. And in terms of SVM, support vector machines, we would have SVM serial tools. But of course, now we are in the league of big data and so on, where we have parallel solution tools, where this part is parallel implemented. Let's put that in the learning diagram. Right, so this is now getting more and more to the concrete picture where we are, basically with this. And when you think about now how the algorithm was finding this, it was iterating through the weights, basically going through all the hypotheses here, One of it will be misclassified, then equals 0, no misclassified point, let's report F, done, that's what we do. Okay, but still, there's some probability distribution that we should add, which will help us later in the mathematics of saying what is with the problems that we have with credit cards, where sometimes the credit card approval guy has a bad day or a good day. He will give a label for the same input, sometimes good, sometimes bad. He will also sometimes, or you, all of you, would go to Netflix, look a movie now, and look a movie in 1 year, and would give a rating which is sometimes this, and sometimes that. It's the same movie, it doesn't change. But you as a person changed, maybe, and give a different label. So you see, we're going towards a kind of out of math way that, you know, a function has always the same input, reports always the same output. And that's not what we want in machine learning. We have the same input, different outputs sometimes. Very hard then to create a function out of it, right? So function approximation is at the end, how we come to machine learning and so forth. However, the future input, that is something what we want to do, and which is helping here a little bit. We put a probability on this. We say there is a certain probability space that these target function has created this. They just don't do it. This is this pattern idea, right? This is not something which is completely arbitrary, like the random number generator, right? This is something which has somehow a probability distribution. It's a notion of statistics that says there is some pattern behind this. Could be long tail, doesn't matter to us. It could be, you know, anything. That is something that we always have unknown, and it remains unknown. It's not important for us. However, we use it to do some things, some statements to say that we can say something about the in-sample performance when we, you know, look at this for the out-of-sample performance. That's why we have a probability related now to it. And now it's a little bit tricky, so get your attention. If you think about, we have the bin here, like with marbles that we have here. Right? This is your out-of-sample performance, your lottery. You don't know. And you have your in-sample. That is the data set that you have already. Right? All the data set we talked X and labeled. That's the only thing we have. The out is basically not there. But when we say that there is a probability distribution about X in general, right, which would be the assumption of the hypothesis set, we say that these marbles in sample would be created by the same probability out of sample. Although we don't know what out of sample is, we never will see that. We assume that probability. And this is the assumption in mathematical formulation that we believe there is a pattern in. If we now have a random number generator, this would be completely used as probability. So then basically this all would be not working out and we can go home. However, we put a probability over X, helping us of saying, well, when we have basically here the kind of error that we basically in sample, like this misclassified point, right? This will say something that we have for other marbles, which will come blue or green here. We will see that the probability would be probably with a green here, and probably with a blue here, for future points, right? And that's an important part. The probability of future points. There are blue points here. When you have already so many we learned from in sample, there is not a probability very likely that the blue point will be here, right? Or here, or there. So it will be somehow related here. And the same will be done with green. Right? So green will be not somehow suddenly here, although it's a hard measurement error, happens in practice, outliers, no problem, we can clean the data and then we have a good data set. But basically this captures the essence of machine learning. Can we say something out of sample? And now I've done this, you can do it also the other way around. When you say there's a pattern out of sample, we can approximate it with the in-sample performance. And we have lots of samples in sample already done. And this is your factor n. If your in-sample is too small, the exam is just one question, then you can do not a statement about the exam that is to come. Right? You just have one question. But if you have 20 questions here, you can say how the basically exam outside will look out and to say something. And this is where the probability is coming to the rescue. It's a nice property borrowed from statistics, admittedly. It's not necessarily being invented in machine learning, but helps us to say we can really learn. And we would say this is basically this term, that this E in sample quantity, something we can always measure. We have the sample, right? We can always measure the labels very closely to the outer sample, and it will track nicely. This is one part of the learning problem and one part of the learning aspects. And there's a second aspect to do, which we have to cover, which is a little bit more theoretically. Sorry for this. But it's like something that will help is all the hypothesis, if you remember. So, because now what I have to tell you is also it is impossible to learn the right function. Again, yeah, short question. Yeah?
How do we clean the data? We have to clean from these measurement errors.
Outlier removal. There are certain just methods that you can use. If scan is one of it, it will detect very easily if you go through the data set that this is definitely an outlier. That cleaning mechanisms that is typically very easy to do. Of course, not 100%. There will be always measurement errors which seem to be very much accurate data That's where the 100% problem comes from. That's why you go back to 95%. Some of them you cannot clean, but it's a term we come to as a noise, and then we talk about it a bit. So, right. So the problem we're tackling now, trying to, is basically, and this is I know it's a little bit, let's say, a bit much, but think about in university lecture we have now 4 lectures, we'll go into details, something we cannot do, just for you to capture the essence that learning is possible. But however, if you think about the hypothesis now, you can assume anything on this probability. There could be any line here, right? And all of them are hypotheses. You come to the factor m here, which is infinite in learning theory. So it's impossible to learn a function. However, there's a probability, we have a helper. There's already one part of it. And the union bound here is a helper which helps you get the worst probability of all of them. And if you do this math a little bit, it's lots of math chains. And you would say the bad event is basically where you say it could be all the worst cases add up. Right? And I have a visual expression which makes this very much. But this is interesting that, you know, the E in from this interesting one that we pick tolerates, basically differentiates from the out-of-sample performance more than a tolerance, is basically smaller than this interesting probability, but here's a factor m, and this factor m is loaded because it's basically infinity. And this is a big problem. We have to tackle in learning theory with this part. So where we say it's approximately that this in-sample performance based on our probability notion deviates from the out-of-sample performance more than a kind of small tolerance, not 100%, as we said. There's a small tolerance we allow, and this is smaller than this massive probability. So there must be something which is knocked down this factor n. We have to get away from the infinity. And there's a nice visual part of it which shows this very nicely. Small question, yeah.
Yes, small question. Why must it be bigger than the tolerance?
Sorry?
Why is the in deviates from the out more than the tolerance?
Tolerance.
Yes, why bigger?
It's basically that, well, you have the minus and the concrete value of it.
Should it be less than the tolerance to be accepted as a probability or not?
Yeah, because that is a probability notion then. And then you again have it smaller than on the right hand side. So you would say that this approximately says that there's something happening which is, acceptable. So it's basically, because the out of sample is here minus, and then it will be basically bigger than the tolerance, you would say, okay, that's not what we want to go. And so the other part around this is this, then what we need as a helper to say, well, let's knock down this to be on the left hand, a nicer probability. Maybe it's better when I have it with the visualizations that will be coming up, when this gets more clearer. It has something to do also with the quantity of the samples, so it's n, factor n for big data problems. If you think about the probability here, and n is a big data problem, that could be also helping. It's a minus exponent, so it's quite also interesting and plays to in the game. However, I don't provide here a tutorial of the statistical learning theory in detail, right? So there are some slides if you want in other tutorials on my website where I go much more deeper. But here in this course, it should be good enough to basically say that we believe there's a pattern in it. That's a mathematical formulation of it. And we know by using in-sample and working on in-sample, we have something that we can say out of sample. So how that looks like, right? And this is the idea that is behind that. We would say the probability of the red points and green points is somewhere here, which helps you also then with this notion, right? So the out of sample performance, even if you don't know, we believe the red point would be not really here and the green point very here. So this is what it helps to establish that. Still, of course, it doesn't solve the M problem, right? This is another problem we solve later. But the assumption here that this actually holds true is already something which we can establish. So the left side is okay. Now, basically, we have still the problem M is infinite. We can learn any function, right? So what is the function now that actually makes that happen? You can go on and so on. So we can measure this with the error function, how good basically all these different lines are. But going through all the different lines, infinite number of lines, that would be also not really the way to go. However, we measure the quality, for instance, with a error measure of a pointwise error, square error. What you can do always with h of x is your hypothesis, the one you currently learn, the learning process, the one line, And then of course you have your y, the kind of learned f of x, and then you have an error measure. So that's something what we already basically done when doing this, going through, and is often used, the pointwise error measure. However, this is much more interesting than to think about also how we cope with the different inputs when it comes to the aspect that I said that the same input, the same that is going to add from x, is giving a different y, basically, which is not possible. So we also have to put a probability over the space of this, making it a target probability and not a target function. And this differentiates machine learning massively from target function approximation. Right? We go one step ahead because basically with the error measures we see in practice that there are some situations where even the error measure could be good, you cannot learn it because it's kind of stupid input. Right? The same function always except the same axis gives the same y. Why it should suddenly give another y. And this is then done by putting the probability over x given y, and then you have this noise factor inside. Right? So this captures the essence, and sometimes you have data sets which are mathematically not plausible. So this is a very important notion that we have to carry around with us. And the example was here basically this error measure. This was basically our error measure we defined here in the perceptron. We always could see basically if this line is not really, or if this point is on the right side of the line. So testing and training, how it influences the learning is another part where we have to think about, because now we're going to the idea of how knocking down basically this error in sample, because we want to basically get this smaller and then think about how we can do it. So we knock down E in. Right now we just said E in sample tracks E out sample, and so when we reduce the error in sample, the hope is that we reduce the error out of sample. Right? So this is the kind of ideas that we are going for, basically in the next couple of slides. So testing is very simple. When we test the data point, basically we have one hypothesis clear, but here we have m hypotheses which we have still to think about, right? That's a problem. So we're training on them, but always with different m hypotheses. Not so very good. So we're doing this with training and testing, so this is just for getting the formalization right for the different processes that we have in machine learning, right? And the test set you see is already much more trivial than the one from training. And these are the different phases we already looked at. So, and this is a key essence, and basically that's the output of 4 lectures of the university normally, that you can take aware that learning is feasible, but only in a probabilistic sense. Because there will be data sets where the same x gives you many different y's. And this is impossible in mathematics, that's why we need something which is basically an assumption about generalization, and this helps you with saying E in is something that we always can do. We can always evaluate this and say there's a proxy for this out of sample, because we're interested in this, but we don't have that, but we want to achieve that. E out of G should be very small. And so with this, basically we would say we have this learning, and would go with 2 parts and say, the one is, this should be very close and tracking each other. The other one should be the E in sample we try to get lower with the learning algorithm that we would see with the perceptron already, in order to knock down E, and automatically our model will be behaving also with less errors out of sample. And that's an interesting part of the generalization theory in machine learning, very important, because otherwise we would not go to machine learning. Right. Of course, it's a little bit of a kind of mathematical field, and I see how that, of course, is basically now needing really lots of university lectures to get the essence of it. Just for you, trust me on that basically we can learn by giving this assumption. And this is interesting. And the next step we do, this is a theoretical assumption. It's called the Höfting's inequality to learn. Then the practical thing is we do the perceptron learning algorithm of getting the E in error on a particular hypothesis close to 0. Knock down this error, right? As told. And this is our practical result we do with the algorithms. Now we have still this infinite spaces problem, which is another part of the theory, which now was really a big breakthrough from Batnik Cheronenkis. There's even a BC dimension and so forth after him about model complexity. I go here a little bit quicker because we're also going towards the end of the lecture. For you, important is just the essence that M is something which is infinite now, but through some interesting assumptions here, when you look at it, you will agree with me that in most of the cases, the hypothesis that we pick will be unimportant, because there is no point. Right? If you think about the line, if it's this way, that way, there are no points there, it's pointless. So the idea of the interesting thing that they did with this, the union bound was a bad assumption. Now the good assumption will be there are less basically problems here, because most of the time we will have the same, the hypothesis having the same output for the samples. This is a carry away message where we now go and shift the view. We will say, okay, let's then have an in-sample quantity. We are just interested in the data that we have in the moment to mitigate with this M hypothesis problem. That means they are, all these models by far overlapping, right? So they're not all the worst case scenarios. Like here, the union bound really says they have no overlaps, completely undoable. But we say that our models somehow overlap all the time. So there's something already which is less than infinite. There's some pattern to discover. And this is a breakthrough that really Cherenkis did with the bound, which is a big step in learning. Putting this, let's say, Höfting inequality was just for one pick of the marbles. It's a probabilistic notion from statistics. We have to do the union bound because there's a learning problem with lots of marbles, lots of M hypotheses. But the union bound was a mathematical helper of saying worst case, I want to classify, or so. But we have seen in the line that we're playing around, also in the animation, the line is mostly really right and covering lots of space with lots of overlaps. And this is then actually the essence of it, that the doubt space of M infinite hypothesis, if you will, can be narrowed down. And we basically narrow that down by putting the emphasis of the number of points you will basically wrongly classify. And this is a notion called dichotomies. You see in this moment, when we cross the point, right here it's irrelevant, but suddenly there's a point. In this point, we report it, that there's some hypothesis, there's something changed. And with this, we have another hypothesis that matters, all others are unimportant. But with this, the number of M you can reduce to an in-sample quantity with all the M's, of course, right? Sometimes you have to, of course, different colors, but it's an in-sample quantity N instead of infinite. This is a takeaway message, really then what basically came from the theory, from learning, and it's called Cherenkis inequality. Can we really learn? And which is a modification then of the Höfting. And it's called the characterization of generalization. We are really able to learn in a probabilistic sense. And this was kind of 6 university lectures going through in a very short way, just for you to understand, okay, basically it is a proof that we can learn. Still, there are some aspects of it which are then related to the model complexity and so forth, where I think that maybe it's also time to break, right? Or what?
If you wish, maybe. Yes, and we continue afterwards.
Yes, I think so. The courses can be a little bit flexible from the times. It's the same audience anyway. So I think it's a good point to break, where we talk about the VC dimension and so forth, and a little bit of the notion. Just maybe one video before we stop here. So this will be a notion, the VC dimension is the Cherenkis dimension. It has something to do with when you learn, you knock down E in, as we said. But there will be a problem called overfitting and so on, that at some point in time, actually out of sample will grow huge. That is a quantity that we will never know, right? It's not obvious to us, but we will see that in practice. When we have a model and we learn that to a certain point, we will always see that, and we will be happy and say, oh, we can net it down to 0 error in sample. But then you deploy it in practice and see, oh Jesus, it behaves very badly outside. And this is something where we have to talk about this overfitting and so forth, where we'll talk about in the next section about when we talk about, the kind of overfitting example. So I would say we take the video as the beginning of the next, and then we can, break now. How long is the break actually?
It's half an hour.
Half an hour. Okay. Let's see you in half an hour. Thank you very much.
Yeah.
And all the things are actually there, right? Sorry? temperature is somehow a little bit less. So it's an extreme advanced field of convolutional networks, and it's for introduction kind of very advanced topic. So basically have some time at the end to
Couple of questions.
yeah, sure, go ahead. But, maybe a drink would be good also. So let's go. Yeah.
Το MPI έκανα δάμε και δάμε εντάξει, τις κάρτες του Περέι, το θέμα είναι να φτιάξεις μια κάρτα να το ανοίξεις σε ούλα και μετά το κάθε να είναι κομμάτι. Το θέμα είναι τα μήνυμα στην ούλα και να το πάρεις το οποίο θέλει να βάλεις στη δουλειά και να σου λόγια στην ούλα. Αν πάει κάτι σε ένα τέτοιο φιλοφύσιο να κάνει το πρέπει να το περιβάλλον πρέπει να
Μάλιστα, ωραία, ωραία. Κάτι καλά. Ποιο είσαι, Σιμών και έξι.
Τον έξαρο, τον
πάντως, ποιο το συνοδυνάνε, δεν έχει σημασία.
Εμένα να σε πέντε, είναι μεγάλο δέκα.
Είσαι
Das heißt also, es ist nicht direkt eingezeigt auf den Text, sondern es ist eher das Problem der Durchstaffelung, dass wir immer weiter aufrühren. Wir sehen immer weiter irgendwie, dass irgendwie jeder einzelne Punkt zur Seite so machen, wie wir das und dann in den richtigen Exampunkt, dann nur Punkt, das auswendig war, das kann sein, weiß ich, 2 Jahre. Aber das ist das ist ja auch schon 10 Folien, da wirklich teilweise
Zweite Frage wäre, Sie haben da beide Dinge gesagt. Die erste war, ein Pattern. Ja. Wie könnte man das vom Einzigen machen? Gibt es eine Information, wo ich den Sachen so eine Hilfe für Studenten habe? Und dann auch die Entropie, die dann viel kommen, das ist
Entropie ist schon mal was, das
ja.
vorher analysieren, was ist Informationsgehalt. Ja, und dann geht es dramatisch.
Also immer so eine große Binary hat keine Ahnung, was das ist. Also bevor man was für Maschinen kann man das noch